Oh, welcome back. We're looking at an example of calculating the moment of inertia about the centroidal x-axis. And if you see the picture, you hopefully immediately recognize it. It's a composite shape, right? So composite shapes require us to do some calculations more than once. Not a big deal. So let's kind of go through the markers for me. So the first marker is the fact that I have to find out about its centroidal axis means I have to find the centroid of this shape, right? So it would be easy to say, well, let's kind of follow what we said we're going to follow, which was where we'd identify the x and y axis first. So, and I place imports on that because we're getting ready to have to use it right away. So that's pretty nice drawing. All right. So it would be easy to say that it is a symmetrical figure. There's symmetry. I mean, we can fold that bad boy in half at the 40 millimeter point. So we'll probably take advantage of that. In fact, I'll go ahead and just write that down. I'll write over, where do I want to do this? So we'll hold on that piece of information right up there where it would naturally be. So clearly there's some work being done there, right? So it's symmetrical. So I know it's not even close to being perfectly drawn, but just pretend with me that the centroid lies on this line somewhere, right? And that distance is, well, the object is at widest area 80 millimeters. It's a symmetrical object, so or 80 millimeters, so 40 millimeters. Okay. All right, but we do need to find the capital Y bar. So our process has been, and I'm going to continue to do it that way, is to break this into two known shapes. So I'll use rectangle 1 and rectangle 2. So area 1 is equal to length times width. Probably seen this in a couple videos already. That's 80 millimeters times 20 millimeters. 80 times 20 is 1600. And so that's millimeters squared. Area of rectangle 2, also equal to length times width. Also fairly simple, 20 millimeters times 60 millimeters. 20 times 60 is 1200 millimeters squared. We'll use the table that we have been using. Area, shape 1 and shape 2. So we're not going to do the X bar. X bar is 40 for both of them. So X bar over R is 40. We kind of talked about that, right? But lowercase y bar we will do. Lowercase y bar. So lowercase y bar for object 2 is, since it's a rectangle, it's halfway between the bottom of the object with top object, so 30 millimeters. That was for area 2. I'm putting in the right place, I promise. For area 1, you have to get up to object 1, so it's 60 millimeters from the x-axis to the bottom of object 1. And then object 1 is also rectangle, so half of the height of that is 10. So y bar is 70 millimeters. A y bar column, that's 1600 times 70. Yesterday that came out to be 112 millimeters cube. Hopefully it comes out to be that today. And 1200 times 30 is 36,000. There are two summations that we have to take. The summation of the area. 1200 plus 1600 is 2800. I like the easy ones. And then the summation of area times y bar. 112,000 times 36,000 is 148,000 cubic millimeters. And we know to find capital Y bar, that's the summation of A y bar divided by summation of A. 148,000 cubic millimeters divided by 2800 square millimeters. And if you do the arithmetic for that, you put in use your abacus, you get 52.86 millimeters. So that's Y bar, capital Y bar. All right. Let's go ahead and draw that in while we've got it, right? Because we said that pictorially that's important. So 52.86 is like right about right here. Let me erase that, and I want to stay with try to stay with the dotted lines anyway. And okay, all right. So if we look at the table, so this is very important. You cannot blindly, well, a couple things. You can't blindly follow the table. There's a piece of information that you need to know. The piece of information that you need to know has to do with this a theorem called the parallel axis theorem. Okay, so we'll talk about what that is. This is a composite figure, so you would expect to be some more composite work. Okay, so here's what the parallel axis theorem says: that when we are calculating the inertia about a centroidal axis, we have to take into account the distance between the centroidal axis for the composite figure and the centroidal axis for each individual figure, right? So looking at area 1, everybody look at the whiteboard real quick. Looking at area 1, here is the centroidal axis for area 1, right? I mean, it's as we described over here, it's 70 millimeters up and 40 millimeters over. And here is the centroidal axis for area 2, right? It's 40 millimeters over and it's 30 millimeters up. All right, so we have to take into account the difference between where the centroidal axis for the composite figure is and the centroidal points of symmetry, not points of symmetry, the centroids for each of the individual figures, right? Which you wouldn't necessarily see that if you were just looking at the table. You also have to take into account the parallel axis theorem, and so we're about to talk about that. Okay, all right. So here's kind of the deal. To find the moment of inertia about the centroidal x-axis, we're going to use the formula that's given in the table, which is 1/12 times the base of each figure times its height raised to the third power, plus the area of the figure times a distance raised to the second power. Okay, let me kind of get this all squared away. It's a composite figure, so we need to do that for each piece. And so this has 2 parts to it, so I only need 2 pieces. I think one of the homework problems has 3 or 4 parts, so you have to do this 3 or 4 times. One for each piece. Let me get it right up here, then we'll go back and look at it. Okay, so then a moment of inertia about the centroidal x-axis is equal to this formula for part 1. I'm going to change colors, then go back. This is for part 1 or piece 1. This is for part 2 or piece 2. Okay. All right. stick with me. It's green. All right. So I'm looking at part 1, 1/12 times the base, which is 80 millimeters, times the height of part 1, which is 20 millimeters. Now I have to cut, now I am coming, raised to the third power. Now I'm bringing into play the parallel axis theorem. The parallel axis theorem essentially says that I now need to take into account the distance between the centroidal axis and the centroid of the figure. Okay, so look what it's made up of. It's made up of area and a distance. So the area is the area of the figure. So the area of figure 1, we did that earlier. That's 1,600 square millimeters times the distance between these 2 points. Times the distance between the 2 points. Times the distance between the 2 points. Okay. I'm going to go back and call this D1 and D2 so I can mark it. Okay. This is D1 right here. D1. How far is it from the centroidal axis vertically between the centroidal axis and the centroid for figure 1? Right? Notice that these two axes are parallel. That's where the name of the theorem comes from. Parallel axis theorem. These two axes are parallel. So from the x-axis up to the y bar, we know that it's 52.86 millimeters. From the x-axis all the way up here to this point is 70. So 70 minus 52.86 is 17.14. So D1, the distance is 17.14 millimeters. So I'm going to just go down and write that in real quick so I don't forget it. 17.14 millimeters, and then that whole value is squared. And so that's part 1's input into this whole thing. Okay. All right, part 2. Part 2, same idea, 1/12. The base of part 2 is 20 millimeters. Height of part 2 is 60 millimeters. We raised that to the third power. Now we need to bring in that factor, right? We have to take into account how far the moment of inertia for the centroidal x-axis is to the point of inertia for that part. So the area we've already collected that. That's 1,200 millimeters squared. Now we need the distance, right? So what is the distance here? All right, so what is the distance between the centroidal x-axis and this point, or the centroid for piece 2? So this time it would be 52.86 minus the distance from the x-axis to that point, and that's 30. So 52.86 minus 30, which I think gives us 22.86 millimeters, where that entire expression is squared. Okay. All right, doing the arithmetic. I think this comes out to be 53. I don't think it does. I know it does. I did the arithmetic yesterday for us. This is 53,333.33 millimeters to the 4th power plus 40. I think it's 400. It's a palindrome, isn't it? It's very close to a palindrome. 47.36 millimeters to the 4th. So that's piece 1. Plus over here in piece 2, it's 360 millimeters to the fourth. Let me erase that because we know that's, I've got a little bit more to go there. And I'll erase the exponent 2 to make it look like a 4. There we go. Plus 627,095. 627,095.52 millimeters to the fourth. And if you add all that together, you come out with 151,0476.213 millimeters to the fourth. If you're looking in the back of the book at the answers, it gives it, probably gives it in scientific notation. Something crazy, I'm sure. But and this is the way I'm going to leave mine. All right, so before I erase this, I want to make sure that we get it, right? So we're looking, the two concepts here. Since it's a composite shape, we need to take into account each of the pieces. That brings into play the parallel axis theorem, which essentially says, what is the difference between the centroidal moment of inertia axis and for the composite figure and the centroidal moment axis for each of the individual figures. Let me pause for a second. All right, so I came back real quick because I wanted to talk about what the next question would be. All right. So the question could say, what about this? What about calculating the moment of inertia? I'm sorry, the moment of inertia for the centroidal y-axis. All right. I mean, if I had to do that, what would I do? I mean, if that were the question, which probably is, let me double check the textbook questions, see what they are. Yeah, in the textbook questions, you have composite figures where you have to look at the moment of inertia with respect to both the x and the c. I'm sorry, the x and the y-axis of the centroidal axis. What would we do? So I'm not going to work the whole problem out here, but I do want to talk about it. So we still have to go through this, right? So the inertia about the y centroidal axis would be equal to 112 b to the third h. Remember how I said in the earlier portion of the problem, all we do is switch the exponent for x and y plus a ad1 squared. So we're going to talk about that again. So this was for piece 1. And then 1/12 b to the third h plus ad2 squared. Okay, now looking at the figure, let me erase a couple things. Let me pause and erase a couple things. So when I unpause, what's going to happen is the whiteboard will be fairly clean, so I can point out a couple things. Okay, so hold on just for a second. All right, so I've kind of cleaned up our drawing a little bit. Because I want to talk about this piece and this piece for this problem. The problem statement for the piece that we're talking about right now is calculate the moment of inertia about the centroidal y-axis. Okay, so again, notice how I've switched just a reminder, I switched the exponents so that we could talk about this y part. We're looking specifically now at the distance. So there is no distance, right? There is no difference between the y distance. I mean, d1 is equal to 0. These are in perfect alignment. right? I'm looking at piece 1 and the centroidal y-axis, right? There is no distance between them, right? So there is up and down, right? Like we used for the first problem or the first part of this problem, but there's no difference between, or yeah, no difference in the distance left and right. So this term and this term would be 0 in this problem. Won't be true in a couple of the homework questions. I mean, I'm looking at like a question that looks like, hold on one second. I'm gonna pause so I can draw it.